Greetings. In this video I'm going to prove Lebesgue's dominated convergence theorem. The theorem says that if we have a sequence of measurable functions fn converging pointwise to some function f, and furthermore if each fn is dominated by some integrable function phi, and here we are integrating over a measurable set A, then the limit of the sequence of integrals is equal to the integral of the limit. And here, of course, the fact that fn and f are integrable follows from domination by an integrable function and the fact that they're measurable. In this proof, I'm going to use the following results. First and foremost, Egorov's theorem, which says that if we have a domain of integration with finite measure, and a sequence of functions, of measurable functions converging pointwise, then for each positive real number, delta, there exists a subset of X, the domain of integration, with measure less than delta, such that Fn converges to F uniformly outside of X delta. Here I stress the fact that the domain of integration has to have finite measure. In Lebesgue's dominated convergence theorem, we don't need to assume that the domain of integration has finite measure. So in order to use Egorov's theorem, we'll have to find a suitable subset of the domain of integration. I'm also going to use σ-additivity of the Lebesgue integral, which means that if we partition the domain of integration in a sequence of measurable sets, then the integral over the whole domain of integration is equal to the series of integrals over each of the parts. And finally, I'm also going to use the absolute continuity of the Lebesgue integral. Which means that for every positive real number epsilon, there exists a positive real number delta such that for any set of measure less than delta, the integral is bounded in absolute value by epsilon. Absolute continuity roughly means that the integral is small if the domain of integration is small. The idea of the proof is that we are going to partition our domain of integration A into 3 sets, in each of which we are going to use the 3 results I've just mentioned. So let us start with a decreasing sequence of positive real numbers converging to 0. For instance, the reciprocals of natural numbers would do. And let us define a family of sets A subscript m, which are going to be the sets of points of A where the value of phi lies between am plus 1 and am. This is almost a partition because f is non-negative, phi is non-negative, and so the difference between A and the union of these AMs is just the set where phi equals 0, and we can apply the sigma additivity of the Lebesgue integral to this family of sets, and so we get that the integral over A of phi is equal to the infinite series of the integrals of these over these sets, over these subsets. Of course, they are measurable subsets because phi is integrable, in particular measurable, and this is true despite the fact that the AMs are not exactly a partition, because outside of the union of these AMs, phi is just equal to 0. So it follows that for some natural number capital M, if M is greater or equal to M, then the infinite series, the remainder series from M equals capital M to infinity of these integrals over the AMs, this is less than some given positive real number, which I'm going to choose as epsilon over 5. And we can take the unions. We can take unions of these AM and define another family of subsets, A superscript capital M, to be the union from M equals capital M to infinity of AM. So in terms of this family, this infinite series is just the integral of phi over A superscript capital M. So the integral of phi over A superscript M is less than epsilon over 5, provided that capital M is sufficiently big. Now we note that each of these AM, A subscript M, actually has finite measure. Well, this follows from the monotonicity of the Lebesgue integral, because in AM we have phi greater than AM plus 1. So the integral of AM of the constant AM plus 1, which is AM plus 1 times the measure of AM, this must be less than the integral of phi over the same subset. And so it follows that since phi is integrable, the measure of AM is finite. Thus we have a subset of our domain of integration with finite measure. And in particular, the complement of A superscript M also has finite measure. So now we can apply Egorov's theorem to the complement of A superscript M inside A, which I'm going to call B, and we thus obtain a set with measure less than delta, which this delta we are going to choose appropriately in one moment. The set C being such that our given sequence of functions Fn converges uniformly to F in the complement of C relative to B. And this delta we are going to choose according to absolute continuity of the Lebesgue integral. And we are going to use absolute continuity with respect to the integral of phi. So we'll choose delta such that if the measure of a given set X is less than delta, then the integral of phi over this set X is less than, again we'll use the same value as before, less than epsilon over 5. So to prove the theorem, we must bound the integral, or rather the absolute value of the integral of the difference fn minus f over the whole domain of integration. This, of course, is less than or equal to the integral of the absolute value of the difference, and we have partitioned the domain into three sets: a superscript m, c, and b minus c. And so we want to bound this for sufficiently big n. Over am and b minus c, over am and c, we can use the triangle inequality, because fn and f are both dominated by phi. We have that this part, the integral over am, is less than or equal to 2 times the integral of phi, and the same thing for this. For the integral over c. And we have already bounded these terms, because c has measure less than d, so this is true for c, that the integral of phi over c is less than epsilon over 5. And so all we are left to bound is this term. But inside b minus c, our sequence converges uniformly. So this means that there exists some capital N for which, if n is greater than or equal to n, we have for any point the difference is less than in absolute value. And here again we are going to use epsilon over 5, and this division by 5 will become clear. And so to bound this term, we use, and we'll get that this is less than or equal to the measure of the domain of integration, which is b minus c, times the bound for the function, which is epsilon over 5 times the same measure. So now we use the bounds that we already have for phi, and we get that this expression is less than epsilon. Provided, of course, that n is greater than big N. Thus we have proven that the integral of fn minus the integral of f converges to 0, and we are done.